Okay, I think we can go ahead and start, and the people can keep joining. One way or another, this is also being recorded. So let's start. First of all, thank you very much for joining, and let's get straight ahead. My name is Diego Rodriguez. I'm a CFD applications engineer here at SimScale. I have a background in mechanical engineering, and I have experience in CAE, mainly working with computational fluid dynamics, which is what our workshop will be about today. So about this workshop, we're going to start with a sort of brief introduction about what this all is about. I will give you a quick introduction to post-processing, but if all of you guys are in Formula Student, I guess you have some experience here. Then I'll walk you quickly through the graphic user interface of ParaView so that you're familiar. And we're going to start a live demonstration where I will show you how to post-process the results for a FSA car simulation. And at the end, we can have a short Q&A if any of you have questions. So about this webinar, the aim is to basically get for you guys to get an introduction to post-processing with ParaView. You will get familiarized with some of the main and the most usable functions that ParaView offers. And this is obviously done through this live online webinar, and there might be more to come. So why don't we start looking at post-processing? Basically, post-processing is after we run a simulation, we have enormous amounts of data that by itself is unusable or ununderstandable. So post-processing is basically how we convert all this data into something that we can understand and interpret and manipulate to eventually make certain design decisions. So we can extract the data, we process the data, and we manipulate the data according to what we're looking for. In this case, we're going to be using ParaView, which is an open source tool. It's quite powerful. And what is nice about post-processing with ParaView is the structure that it permits, that it allows to use. So this is basically our simulation data, and we can start applying filters either in series or in parallel. So after you apply a filter, you can apply a new filter to that one, or simply go back and you can have as many as you want in any direction. So let's start by looking at the GUI. I'll show you the most basic elements so that you know what we're looking at. First of all, we have the main toolbar, which just gives you access to all of the functions in ParaView. The rest, or most of the other buttons, are simply shortcuts, but you can do everything through the main toolbar. Then we have the pipeline browser, where you're going to see all the structure of your filters and open foam cases that you have loaded into ParaView, and you can edit and sort of play around with this structure. We also have a panel for properties and information. So in properties is where you're going to modify all the settings of each of your filters. And information is simply some data about where is the open foam case you're opening, or things like these. Then at the top, again, you have something where you have the time control. So it's basically changing time steps. When you run your simulation, you can either only save the last time step, or you can save different time steps along the go for steady state. And this lets you browse between those time steps you're saving, and maybe you want to compare. Then we have the shortcut for the camera control. So here you can simply select, for example, which axis you want to see normal to, and if you want to see it sort of positive or negative, fit to viewer, which are some quick toggles that make it easier than rather panning through all the domain. And then we have the center of axis control. So here you can toggle on or off the viewer of the of your axis. With this one, you can toggle on or off the visibility of your center of rotation. And basically, with this one, when you're zooming into something in particular, and you're going to see this later on in the webinar. The rotation can get a bit weird, so you can select which point you want the center of rotation to be. And finally, the render view. Here you can split screen either horizontally or vertically, maximize your layout or close your layout. With this in mind, we're going to move on to a live demonstration where I'm going to be using ParaView to post-process the results of an FSAE car. I don't know how many of you participated in the workshop for CFD and Formula Student, but it's going to be that same car and that same setup for those of you who are familiar. So when you open ParaView, and in this case, it's important to highlight that I'm using ParaView version 4.3.1. They have newer versions. They have up to 5.4, I think. But this is one that we know is very stable, and you will probably won't get any bugs as it is an open source tool. So the viewer and some slight settings might differ if you're using a different version of ParaView for your post-processing. So let's get started. First of all, when you open ParaView, here you have this button, which is used to open a file. In this case, we're going to open an open foam case, which is the result of our simulation. So this is the file structure that you will get when you download your results from SimScale and extract them from the zip file. And we're interested in opening this one. So you can select it and click OK. And then this will load the foam case, and you will have some information and some things in your properties panel and other in the information panel. So for example, here it says that it's a multi-block dataset. So that basically means that, for example, we have a fluid region, we have different surfaces that are individual blocks of information. It also shows the path where it's opening from. And here you can select which of the mesh regions you want to load into ParaView, and you can also select which of the cell arrays that you are going to load. In this case, we're going to load every single thing because you're going to see it. We're going to use a lot of filter that I'm going to teach you in a minute. That makes the workflow a bit easier when you have everything loaded, so all the blocks loaded. And instead of, for example, if you have the fluid domain and then you want to see the front wing, you'd have to load it again. When we have everything loaded, you won't. So you click apply, and this eats up a lot of RAM, so close to 16 GB, and it takes a while. So I have my case already loaded here. This is not how it looks when you load the case. You will have a very big domain. You'll have your entire domain, the entire bounding box that you defined during your simulation setup, which will load. A useful thing is for you to load the STL, or the geometry for your car. That way, so it's a light model that you can easily visualize and move around. rather than having the surfaces of your simulation results, which can be a bit slower to move around because they carry all the data for the cells. So you open it exactly in the same way. See here, I click the button for open, and simply select the STL, click OK, and it will load the model. So let's start talking about filters. The first one I mentioned earlier that will make our life easier or our workflow easier is called extract block. Basically what this does is, as our foam case is a multi-block dataset, extract block allows us to select which blocks of this dataset we want to extract and visualize. So we can load everything in our foam case. You see we have everything loaded, and then we can individually select which block we want to visualize. So we're going to start by loading only the fluid. So how do you apply a filter? We have two options. You click on your foam case. You go up here to filters, you go down to alphabetical, and you will get the list of all the available filters that ParaView has that can be applied to the item you selected. So we could go here and look for extract block. The other option, which I like better, is in your keyboard, simply do Control spacebar, and this opens up this small window, and you can type which filter you're looking for, and you can navigate using your arrows in your keyboard, or you can you select the filter either by clicking enter in your keyboard or by clicking here extract block. This is the structure that the filter has. It shows you all the blocks that are possible to extract and all the patches. The patches are simply individual surfaces that are associated to the simulation. And this is right now the only option that you would need to modify. Simply make sure that prune output is selected. And we can click on internal mesh, which is our fluid region, and click apply. Again, this will take a bit of time because it's a big mesh. So for all intents and purposes, I've already loaded it here. And again, you will see the entire fluid domain when you click apply. So a very big block. When your fluid domain is loaded, we can move on and start applying different filters. So how I'd like to focus this session is looking at filters that can be applied first to the fluid domain, and then we're going to look at applying filters to the car. That's why I have extracted the fluid block and why I've extracted the car block in two separate sections. So we can start, and one of the main and most useful filters is the slice, which I'm guessing most of you are familiar with. How do you apply it? Again, you can either go through filters, alphabetical, and select your slice. You can either Control spacebar and type slice, or because it's such a used filter, we have it up here in the filter in a filters toolbar. In a filters toolbar. So we have, for example, a calculator, contour. You can hover over it, and it should tell you which filter you're looking at. And so basically it would be the fourth one from the left. It's not highlighting it here, but select the slice. And here you see this is the size of your entire fluid domain. And you have some basic settings here for your slice. It has the origin, so the center where it's going to be, and then you have the orientation of your slice. You can either play around with these buttons, which are very quick toggles to have it Y normal or Z normal. You can fine-tune the location by typing the origin in here, or you can simply hover over it and move your slice. If you don't need it to be in a particularly exact location, this is generally the easier workflow, because, for example, we can zoom here into our car, and let's say we want to take a slice of the car almost down the middle. So here you see we're very close to the middle of the car, and it was very easy without having, to type thousands of digits into the origin. To visualize flow fields, leave crinkle slice unselected and leave triangulate slice selected. I will go into a bit into depth here in a couple of minutes. But basically here you simply can click apply, and you should also uncheck this show plane, because when you're manipulating, if you can see the plane, you end up moving the plane, which is not ideal. So let's see the slice. We wanted it close to the center, close to the middle of the car. We hide the plane, click apply, and we're going to have a slice like this one. When you load it for the first time in your ParaView, if you haven't modified any default settings for ParaView, this will not be the color scheme that you're seeing, and ideally you should edit it. So how do you do that? Up here in the left corner, we can toggle on or off the control bar, the color bar, sorry, and here we're going to edit the color map. Here you have a series of buttons. You can see the mapping data for all your colors. So you can, for example, choose if you want to show more blue. You can choose if you want to see more red. But ideally, we would leave it as a default in general. And to select this color scheme, which is called the blue to red rainbow, which is basically the industry standard, you click on a small heart that appears here, which has the preset color scales, and we select blue to red rainbow, and it applies it automatically. The second thing you should do is change the number of discretizations. So basically, this is the number of colors that you will have in your color map. It normally is 256, and you should generally try to keep it between 32 and 64. The more you have, the smoother your image will look, but the harder it will be to highlight differences between pressures or velocities when you're looking at a slice. So when you keep it low, it's easier to see, and it can facilitate certain design decisions when you're looking at the ground effect that your car is generating, or which is the most critical area under your wing. So that's why we keep it under 32. And now you can click this save button, which means next time you load ParaView, you will load with this color map and this number of table values for your colors. And basically you have to do this for whichever field you load. They're all, or most, are preset to the same color scheme, which is not very nice. So today we're going to focus mainly on velocity, pressure, and we're going to talk a bit about wall shear stress. But then you should select this color scheme and this number of discretizations. Then we're going to modify the color bar, in general the title and the numbers. So if you go up here to your top right corner of the color map editor, you have Edit Color Legend Properties. You can click there. Here we can modify the title. In component title, we should always have the units for what we're visualizing. In general, for like showing purposes, keep the both formats to times. If you're using ParaView 4.3.1, keep the title and the text annotations both to 8, font size 8. Turn them black. And then you can select if you want it to be italic or bold. Then the number format is also pretty important. This is not the default format. You can unselect automatic label format, and we're going to give it this value, which is basically all this is defining the format, but the one we care about most is the last two characters in this case. So after the decimal, after the period, you can define the number of decimal places you want shown in your color map, in your color scale, and the letter will define the type of number. So F means float, which is a number that allows us to have more than one decimal place. And that's why we can that's the one you should always have. And then you can simply modify this, the number of decimals you want to show. You should also keep the maximum number of labels to 5 to keep your color bar clean. And also apply the same format for the label format and for the range label. This range label is the top and bottom numbers that appear in your color map, which define the custom range or the range of the data that you're presenting. And finally, please always change your aspect ratio to 30. It looks much better. You can then click Save here to save these settings. So next time that you load ParaView, it will load with these presets. The only thing that you would need to modify is the title and the component title. And you should do this for whatever field you want to visualize or you want to expose. With this done, we can get a bit more into working with our slices. So right now we have a slice for the velocity field, and we can either show or hide the car. I've clipped the data in a certain range just to highlight different areas, but we can keep it an automatic range, which basically takes the minimum and the maximum number in this slice, the value in this slice, and applies it to the color scale. Slices not only work for visualizing our flow fields, they can also work to visualize our mesh. So if, for example, right now we would like to view our mesh, we can create another slice, and this new slice we would actually check crinkle slice and uncheck triangulate slice. What this does is that the slice that you're seeing here cuts through the cells and is basically a two-dimensional, it's a two-dimensional object. When you select crinkle slice, what it does is that it identifies all the cells that your slice is cutting through and shows the entire cell. So it looks like this. We have exactly the thick cells here, and then we can zoom into our geometry. You can hide the car, and you can inspect your mesh this way. For example, you can inspect the formation of boundary layer, which in this case is quite good. We see a constant boundary layer here. We have good refinements around the car. We have a refinement at the wake. We have the boundary layer for the floor. So it seems like a good mesh, and that's the other use for slices. But within slices, we can use a couple of different settings and more filters that enhance the information that you get from a slice. So the first one would be using a surface integrator, which is called a surface LIC. And basically what this will show us is the movement of the fluid. This surface LIC only works with velocity. I mean, it should be superposed in velocity, and it looks like this. You go up here to your visualization, to the type of visualization you want, and select surface LIC, and it's going to look like this. So here you can see the fluid motion. Because it's integrating the entire fluid domain over the slice, it can make the viewer a bit slow. So if you want to move around, I recommend going back to surface, playing around with it, getting the view or the zoom you want, and then applying the LIC again. And so, for example, here we have these two nice recirculation zones. The surface LIC is not set by default in ParaView, so you will have to load it. This means that any of you who have never used it before will click this drop-down menu and you will not see surface LIC. So to activate it, you should click on Tools, click on Manage Plugins, and you have a list of plugins. Here is Surface LIC. For the first time, you will click on Load Selected, but you should also click on Auto Load. You will have to restart ParaView, but from now on, every time you start ParaView, it will start with the Surface LIC loaded, and you will be able to apply it to any slices that you make. Then the second thing we can apply is a filter, because the surface LIC is not a filter, it's a type of visualization. So this is called the glyph filter, and it's basically going to show us the vectors of our fluid. In this case, the velocity vectors, and it looks like this. Again, it makes sense to show it with a slice of velocity. I like selecting arrows here instead of 2D glyphs because I like how thick these arrows look. The scalars in this case don't really matter because we're showing them black. But the vector is important. Right now we want to see velocity, so this is what it's highlighting. The scale factor, you're always going to play around with it, but in general you should try to keep it in the low end, because when you load it for the first time, it will be huge and completely overcrowd your screen, so keep it low. The maximum number of points, of sample points, is basically the number of vectors that you're showing. In this case, because I have a slice of the whole domain, I chose to show 10, but the default 10,000, but the default is 5,000. And you can play around with that setting to get the density of vectors that you want. And to change the color, the first time you load them, they will be showing one of these field values, probably P, but we want to show it in a solid color. So here we select solid color. And the default color of ParaView is white. So you're going to have to go into your properties panel and scroll down and look for coloring. In coloring is where you can select the actual color for that your vectors will be showing. So in this case, we have black, and it has this nice thick view of the vectors and the direction of our flow. The third thing that that you can apply to a slice is a contour. So in summary, the surface LIC and the glyphs work very nice when you show them with velocity, because they're essentially showing us the velocity and how the fluid is moving. But if we want to visualize pressure, which is a scalar quantity, sometimes it can be a bit hard to distinguish between certain colors of the color map, and this is where our contour comes in. I just realized that I completely forgot to tell you how to select the glyph. So you click on slice, and from this top view, these shortcuts, it's this one, the sphere with the small dots, called glyph. But moving on to the contour, you select again the slice that you have. We're going to visualize pressure for this one, and we're going to apply a contour. The contour is the second one from the left up here. You click on it, and basically you're going to get this view. We're going to contour by pressure. You can only contour by scalars. And how this works is that it will show us isosurfaces on this slice we made. So it will show us a line between every single change of color in our slice. How to do this? The value ranges. First, you're going to delete the default value range, and you're going to select add a range of values. This will automatically detect the scale, so from -603 to +246. But the number of steps is the most important part. These steps have to be the number of colors in your color map plus 1. So if you remember correctly, we have selected 32 colors in our color map for all the flow fields. So the number of steps here should be 33. You click OK, and it adds this table, which is basically the information for the isosurfaces, and you click Apply. And it looks like this. So here we have highlighted the difference between all of our colors in our slice, and makes it much easier to identify where higher or slightly lower pressure areas are. Then the last neat thing we can do with slice is an animation. So to do that, we can visualize our car, and let's say we want to view something like this, and we want to generate an animation of this slice moving in the positive y direction, and basically showing us how the pressure changes along the side direction of our car. So to do an animation, you have to click on the slice that you want to animate. You have to go to View and select Animation View. This will open up this this menu or this settings panel. Here you see that we have the slice that we want selected. Make sure you select slice offset values here, and click on Add. This will tell ParaView that we want to do an animation of this slice with the values of this slice. Next, you should double click on this on your slice. Right now we're going to take 20 slices, and this value is the coordinate normal to the surface, to the slice, where your animation will start and where it will end. So I mean, the car is at 2 meters wide at most. like 1.6 meters. So it makes no sense to go from negative 14 meters to 14 meters. So you would select this to 0.001 just to make sure that you're inside the fluid domain, and then go to around 0.2 meters. This is absolute values. And you click OK. You see here it will show you the values. You can double click on time, and normally the default is that it shows you animation time, but we want constant time because it's a steady state simulation. We don't have any time actually. So select constant time, and this is the number of time steps that you saved for your simulation. In this case, our last time step was 1500, so that's why it's there. Then go to mode, select sequence, and basically the time is 1500, which is the time of our the last time step of our simulation. The start time will be 0, the end time will be 20. This is quasi time. This isn't really time. Just to make sure that it matches your number of frames. In this case, we want to see 20 frames, so 20 slices across our car. Our end time is 20. With these settings set, like this, you're gonna click on File, Save Animation. Here it will tell you the duration of your animation. So if we do 15 frames per second, it's too high. So ideally we could have 2 frames per second and have a 10-second animation, which makes more sense. And that gives you the resolution automatically. Click Save Animation and give it whatever name you want, and save it in AVI format, which is actually the only real video format that this supports to export an animation. And click OK, and it'll show you a dialog box saying that that the pixels, the quantity of pixels needs to be edited. Just say OK, and it will start animating your slice. You will see how your slice moves, and then you will be able to see your video like we have here. For all intents and of time, I will skip showing the video, and you can try it out for yourself. And I'm going to move on to another filter we can apply to the fluid domain called the Streamlines. These Streamlines basically are showing us how the air moves around our car, and we can see it in 3D instead of just a 2D plane like a slice. So the settings for this, again, you have to go back to your fluid region. You have to select the Streamlines either by clicking Stream Tracer here at the top shortcut, or Control Space and typing Stream Tracer. This is integrating our results over the domain. We have it basically starts in a point. We have the point source. So in ParaView 4.3.1, it's hard to see the point. In newer versions, it's actually showing a big sphere with your radius, which is very nice. But in this case, you can simply select the origin that you want your point to be in. You select the radius of the point, the radius of the sphere or circle through which these streamlines will be detected. Then you can edit the number of points you want. So in this case, we have 50 streamlines, or 50 points being integrated over that 0.5 radius circle. We're integrating in both directions, so you can either integrate upstream or you can integrate downstream. but right now we're interested in viewing where the flow comes from and where it goes. And the maximum streamline length is, again, a distance downstream and a distance upstream from the point location that you have selected. And you can make it as high as you want. If the default setting you think is too short, you can increase it. Here I have shortened it because our domain is pretty big. So I'm just interested in sort of a little bit upstream and a little bit downstream of the car right now. Okay, and when you click apply and you will see this, you can select if you want to visualize velocity, if you want to visualize pressure of your streamlines. Right now we're visualizing velocity. And there's a pretty neat filter that you can apply to the streamlines that will make them really thick. So this filter is called Tube. So that one, you can't find it in the shortcuts here. So you would have to control space or go through filters and alphabetical. I select Tube and I apply the filter. What this does is that it will thicken our streamlines. So the radius 0.007 should be good enough to show you thick streamlines, but not ones that are too thick. The default value is very big, and again, it will overwhelm the viewer that you're seeing, and you will only see like a massive lump. And then those two are basically this is the only relevant parameter that you can play with for the tubes, and this is how they look. So it's basically thick streamlines, but it looks very nice to like, get some nice pictures or better visualize what your fluid is doing. We can see a rotation here after it leaves the rear wing. I'd like to take this chance to highlight that I don't know if you notice, but the rotation of my car is very weird. The center of rotation is not sort of in the middle of the car. It's somewhere behind the car, and this makes it very annoying. So this is the perfect example to show you that if you select this button in the editor of center, you can select the location where you want the center of rotation to be. So right now I selected the head of our driver, and now it makes sense, and I can more comfortably play around and view our car and their streamlines around the car. This is basically the most interesting things you can do with your fluid domain. If I may go back and highlight one thing about the surface LIC I forgot to mention, is that when we're visualizing the slice, you want to when you apply the slice, it looks when you apply the LIC, I'm sorry, it seems very overwhelming. So it doesn't look as nice as it looks right now. It looks like very thick and very populated by these lines. So in the properties editor, you can select you can click on this small wheel, which will expand all your options, and it's a lot of options, but you just have to look for one called intensity. Lick intensity. Here, set it to 0.5. This makes a good balance between visualizing the motion of your fluid and the actual colors of your color map. But right now we can move on to the car. Here you can, for the surface LIC, you can play around with settings to enhance contrast, but I leave that up to you to select the visualization you like most. If we move ahead to the car, we're going to use extract block again. So we select our foam case, we apply an extract block filter, but in this case, we just select all the patches for the car. So this will load our car with the field values that have been calculated on the surface. Right now we're visualizing wall shear stress. And so what you get with the car, here there's you can also apply a surface LIC to your car surface, which looks pretty awesome. But you have to be careful because velocity at the surface is always going to be 0. So if you apply a surface LIC the first time, it will not show it to you because there is nothing to integrate on the surface. Everything is 0. So you have to go into, let's let it load a bit. There we go, and it looks pretty nice. You can zoom in and see sort of the movement of your fluid, of the fluid over your car. But what's important is that to be able to see a surface LIC or an integration over the surface of your car, you have to go into settings and under surface LIC integrator, change it from velocity to wall shear stress. And this will allow you to see this nice visualization we have right now. We can move back to surfaces. And right now we can visualize wall shear stress. We can visualize pressure if we want around the car. And now we are going to visualize drag and lift on our car. To do that, we're going to apply a new filter to the extract block, so to the car here, selecting this. You will control space and look for one that's called generate surface normals. This will exactly generate a normal for the normal vectors for all the surfaces around the car. And to this, it looks exactly like our car. It just now has the information for all the surface normals, because what we want to visualize, lift would be the pressure in the Z direction, and drag would be pressure in the X direction. So that's exactly what we're going to do. You generate your surface normals, and to this newly applied filter, we're going to apply a new filter, which is a calculator filter. It's the first one in this shortcut bar. You click on it. You can change the name here, but here you should, the result array name, we're going to call it drag. And we're just multiplying normals in X times our pressure. The normals in X are a scalar, which you have a list of all the scalars here. So it's normals in X times P. You click apply, and we have a visualization of our drag. If we rescale it to better highlight our results, you see that the leading edges of everything and the nose and the face of our driver feel a lot of pressure in the X direction and generate a lot of drag. For lift, we're gonna do the same thing. So you have to go back to generate surface normals, apply a new calculator, and here it's going to be normals in Z times pressure. And now you see that the red areas in the leading edges are gone. And now if we rescale it again more appropriately, you see that right here we can see our ground effect working and our downforce being generated. This is feeling a lot of pressure in the negative Z direction. So it's a pretty neat, and you can analyze, visualize particular areas. If you want to look specifically at an area, for example, we want to see only the front wing, you can apply an extract block filter to the lift calculator. And so it will look like this. It has the same structure as all the extract blocks, just that you can see we select only the front wing. And we're now seeing lift, but only for the front wing. We can modify our center of rotation here and have that. And you can do it for whatever part. You can visualize it for your rear wing, and it's just about, you know, using extract block and obtaining the particular set of blocks that you want to visualize. I had a question earlier about what was the difference between using simply like loading new open foam cases and extract block. The difference is the workflow. So with this extract block workflow, I don't need to load them again, and I can simply, you know, from the extract block, select whatever is useful without necessarily loading it from scratch. So I feel it's much faster for me to, if I want to see only the front wing, instead of going back and loading a new foam case and loading only the front wing, I already have everything loaded and I just extract the front wing. So I feel it's a better workflow. And yes, this wraps it up for the things we can do with the surface of our car. Again, I leave it to you to explore different settings and different ranges to better highlight your results. Right now, we're going to move to, I think, one of the most interesting parts of the post-processing, and one that gives you maybe the most amount of information. We're going to generate 2D plots over surfaces. So I'm going to take as an example the pressure coefficient graph of the main component of the front wing. So for this workflow, we can start, or we should start by visualizing a slice of the whole domain. And because it's pressure coefficient, I'm going to visualize pressure right now. To calculate the pressure coefficient correctly, I need to know the pressure in the free stream. And although the simulation was set up with reference pressure 0, here the pressure in the free stream it differs a bit. So to get more accurate results, I'm going to show you how to obtain information for a small corner here, some cells here. And with that value for pressure, we're going to calculate our coefficient of pressure. So we're visualizing our mesh, our slice. We load to somewhere upstream where the flow hasn't been disturbed by the car. And up here we have a small, very small toolbar. Look for the one that says select points on. Or simply type D in your keyboard, draw a small square, and it's selecting points within my mesh. As a default, you will not see these values. You will only see the pink dots. So to be able to see these values, you should click on View, Selection Display Edit Inspector, and here in Point Labels, select either, whatever you want to see. The default is that you will see it like this. You will see no information, but we want to see pressure. So the point labels are going to be the pressure associated to that point. That's fine. We see it's around 3.4. So that's what we're going to use to calculate our our pressure coefficient. To remove those, click D again and select somewhere off the slice. Let's go back here. And to the car, we're going to, so I mentioned that we're going to do the pressure coefficient for a place in the main component of the front wing. So start by applying a calculator filter to all of your car surfaces. That way the pressure coefficient is calculated for all your car, and then you can select if you want to see only the front wing or the back wing or the body. So you already know how to apply a calculator filter. We go here, and this is the standard pressure coefficient formula. So it would be pressure minus 3.4, which is our reference pressure, over 1/2 rho, which is our density. In this case, the simulation was set up with air of density 1.1965 and the free stream velocity squared, which in this case is 20. You can you should change the name of your result array to CP. Click apply. And now we have a pressure plot, the information for pressure coefficient on all of our surfaces, of all the surfaces of our car. So to be able to look particularly at the front wing, we're going to use the extract block filter, apply it to this calculator, and select only the front wing, main wing, which gives us this. Change your center of rotation so that it's easy. And for example, I don't know, let's say here we see a very strong reduction in the pressure coefficient, and consequently it's also in a drop in pressure in this area right here. So let's visualize the pressure coefficient along a slice that's applied through particularly this point. So again, to your extract block, apply a slice filter, make it Y normal, orient it in any direction you want, place it wherever you want. In this case, I placed it right across this low pressure area because I want to see what's happening there. And click apply. We are going to get this. That's how our surface looks sliced at that point. And to be able to get a standard wing versus pressure coefficient plot, we have to apply a new calculator. This one is a bit tedious. Keep adding filters, but it's worth it. So to your slice, add a calculator filter. Call it chord, because we're just going to extract the coordinates in all of our directions, because we want to plot against the x direction, against the x coordinates. So from scalars, or yes, from vectors, select chords and click apply, and this will simply store the information for the coordinates of your domain. With this in mind, right now we have our slice of our front wing. To the last calculator here, you're going to apply a filter called plot on sorted lines. So you select the slice, you do control space, and plot on sorted lines. You select it and click apply. When you apply, this side window will open. They will open in horizontal split view, and you will have probably a mess of information because most of the arrays will be loaded. So in this case, be mindful and change X array name, change it to coordinates in X, which is what we actually want to visualize. You can unselect all the variables and select only CP. And now you can see that we have our standard pressure coefficient versus wing overlay, where our leading edge, where we have the stagnation point, we have a CP of 1. And this is quite interesting because if you've seen normal wing profiles, they don't look like this. They have a much smoother CP curve that, for example, tails off and recovers around 0 very smoothly. And right now it doesn't look like this because, and this is very interesting, we're visualizing right now pressure, and because we have the ground here, this drop in pressure coefficient, so this drop is about the bottom surface, is because we have a ground effect. So we have a massive pressure drop here that's not necessarily normal. And then in the recovery area, we have a flap. So it doesn't allow the fluid to recover normally, and the pressures to recover normally. So for our top side, we have this sort of like big drop in pressure because it's escalating, and then there's a very sharp gradient here. And this weird shape is also caused by the existence of our flap behind the main wing. So this is quite interesting to visualize, quite helpful in terms of design decisions. Finally, and before I move on to the last thing I'm going to show you today, let's say you have selected a very nice view of your car. I don't know, you want to compare two different runs, or you want to compare two different designs, and you don't want to sort of have to load everything twice and go through maybe like all the filters again, which can be very annoying. Or if you want to be able to overlay two pictures that are comparable from two different simulations, manually you will never be able to do this, because it's very fine, you know, it will always vary a bit. So we have some very nice controls here for the camera. So right above our viewer in the left corner, we have a button called Adjust Camera. And here you can manipulate the sort of position, focal point, view up, but I think that makes much more sense simply panning across your domain and rotating it in whichever you want. But when you have selected when you have found a view that you really like, or a view that you think is very meaningful for analysis of results, you have two options. You can configure a custom view. So you click here on Configure and assign the current view to this one. Select OK. And now, even if I change the view, I can click on one and it will always return me to the view I want. If you have more than 4 views, or you're going to quit ParaView and do some post-processing another time, you have the option to save the view. So you go here, you click Save, file name, let's say view 1, click OK. This is going to save our view. So right now I change it, or let's say loaded a new one, and I want to see the same view I had before. I load it and it's right there. So that makes it very easy. This is it for today in terms of post-processing using live ParaView. I hope I covered enough material for everyone to be able to do some meaningful post-processing and make meaningful design decisions. If you have any questions, please feel free to ask them right now, or if not, I mean, I can wait a bit if any of you want to ask anything else. My colleague Anna has been very helpful in answering some of the questions that have been asked. Let's move back here. Okay. Okay, so we have someone asking, okay, about opacity. I didn't mention that. Okay, let's start with another one. Okay, now let me answer about the opacity first, and then I will go with a question about visualizing CP over a three-dimensional surface. So how to manage the opacity here when you have selected either a slice or the car or whatever. In your properties panel, you can go down, and in styling, you can modify the opacity to whatever you want. See, now it's a bit transparent, and this can help you if you're visualizing a slice and the car is covering up part of the results, then this is very helpful to play with opacity, and you can do it also for slices. I have a user asking if there's a way to obtain values in a graph, say the CP over a three-dimensional surface. So you can extract the data. Let's go to our CP calculator here, our main wing. When I have this wing plotted, or this value calculated, let's say it's all over the place in the front wing, we can apply a filter which is called plot data. And it is working, but it is more tricky because right now then we don't have sort of one axis against which to plot everything. So I like using a view called a spreadsheet view. So here it has all the information for all the data points on this surface. So if you have a way of post-processing this information, let's say in Excel, or you have your own script, then this does make sense to have the sort of this information over the entirety of your wing surface. But otherwise, it might make more sense, or if you're just staying in ParaView, to make a slice in sort of certain areas of interest and apply the graph like we saw earlier. And Barry, yes, of course, we can also apply the same calculator to the fluid domain. In this case, I just applied it to the surface, but so I'm sorry, Barry's asking if I can apply CP not only to a surface, but let's say to my entire flow field. And yes, I can. It's exactly the same workflow. So you would go here to fluid, you would select a calculator, and we can name it again CP, and you would simply write your formula again, so pressure minus 3.4, etc., and this will calculate the flow field, the CP value, and you can visualize it behind your diffuser, behind the car, behind sort of wherever it is that you need to visualize it. So guys, we've gone a bit over time than what we expected. This is being recorded, so if you don't remember something, when we publish the recording, you can go back and try to see it. I hope this was quite useful for all of you, and that it will help you up your game in terms of post-processing, and that will lead to some amazing design improvements. Being that, this is the end of the webinar. Thank you very much, everyone, for joining, and I hope to see you all in future webinars. I wish you all the best in the design of your cars, and have a good day.